Alrighty, so we want to look at variance and standard deviation. These are part of the central moments. That was definition 4.2. And so these are just particular expected values. Normally we do the variance as sigma squared, and that is the expected value of our x minus our mean squared. Okay, so for discrete, we would have that sigma squared is equal to the sum over i's of x sub I minus m squared times f at x sub I. And for continuous, we have the integral from minus infinity to infinity of x minus m squared f of x dx. And so that's all it is. I mean, it's just that particular expected value. Now, though, what are we looking at? Well, it's an average. When you think about data, I could have two things that have the same mean. Possibly one of them looks like this, and the other one looks like this, and so here's m and there's m. And in some ways these distributions are similar, but in other ways they're very different. And so just knowing the mean doesn't tell me everything. And so we have that the mean is a measure of central tendency. Okay, sort of where's the middle of the distribution? Well, variance, or sigma squared, is a measure of dispersion. And so we just have this idea. We're looking. Notice, what this is. We're taking each x value, and we're asking how far away is it from the mean. Now we're squaring that amount to get our average, as opposed to, we could say, take the absolute value. And I think intuitively, absolute value makes more sense. But it turns out squaring ends up having better mathematical properties, and so that's what we do, is we look at the square of this thing, we call it variance, and but you can see, it's again, we're looking at that difference between some x value and m, and we're squaring it and taking that weighted average. Okay, so that's the variance, and we can calculate it that way, but we could also calculate it slightly differently. So if we take our sigma squared, and we say, okay, we'll do it with the continuous case. The discrete case works just the same. And so I have my x minus m squared f of x dx. Well, that's equal to the integral from minus infinity to infinity of x squared minus 2xm plus m squared all times f of x dx. And so that is equal to the integral from minus infinity to infinity. And if I break that up, I've got x squared f of x dx minus 2m integral from minus infinity to infinity of x f of x dx, and then plus m squared in my integral of f of x dx from minus infinity to infinity. So that's equal to, well, this first one is just the definition of the expected value of x squared. The second one is minus 2m expected value of x, and then plus m squared, because this last integral is just 1. Now, the expected value of x, though, is just the mean, and so I have the expected value of x squared minus 2m squared plus m squared. And so another formula for variance, we usually call this the calculation formula, is to just get the expected value of x squared and then get the mean and square that and find that difference. So that's nice that way. So that's the variance. And let's see. So we've got some properties of the variance. And so if I let y equal the random variable x plus some constant, so I just shift it over. Well, intuitively, all right, I started with maybe this, and then I added, so there's the mean maybe, and so I shifted over by c. I add c to all the x values. So, and maybe that's here. And so I would kind of expect the same picture just shifted to the right. And if that's the case, we would expect that the variance of y equal the variance of x plus c is just the variance of x plus the constant c. And similarly, we have another one where if I multiply x by c, that then the variance here is actually ends up being, well, let me write that stuff in, c times x. That's c squared times the variance of x. Okay, now that includes if c is negative. So for instance, if I have a random variable x, if the variance of x is equal to, say, 4, then if I let y equal negative 3 times x, then the variance of y is equal to negative 3 squared times the variance of x, and so I get 9 times 4, or 36. Okay, and then we have the standard deviation. And the standard deviation we just call sigma. We had the variance, which was sigma squared. So sigma which is the square root of sigma squared, or the square root, standard deviation of our random variable x, the square root of the variance of x. And the standard deviation ends up being a nice quantity to use when making estimates of probabilities, in particular with the normal distribution. Okay, and so I think I will stop that there.